In Chapter 6, we're going to look at some of the energy considerations in chemistry. And so first we're going to define a few things. Alright, so energy is the capacity to do work. Potential energy is energy that's stored somehow, whether it's stored at the top of a hill or whether it's stored in chemical bonds. Kinetic energy is energy in motion, that is bowling ball rolling down a hill, or a broken chemical bond, which is releasing that energy that had been stored. The law of conservation of energy is very similar to the law of conservation of mass. Basically, total energy of a system does not change. You can't create new energy, you can't destroy energy, but you can change the form of energy, just like you can with the mass. Chemical bonds are how we store chemical energy. The lower potential energy in a compound, the more stable it is. So that lower ground state, as we call it, is the more stable that compound is going to be. It also has it reacts to form products, and if you have a lower potential energy in your products, then your reactants are going to be favored. Okay, so if you have reactants and they are going to form products that are lower in energy, then this is going to be favored, or it's likely to happen. So a little more terminology. A calorie, and notice that that's the lowercase CAL, is the amount of energy needed to raise the temperature of 1 gram of water by 1 degree C. A joule is 4.184 joules is equal to 1 calorie. Joules and calories can both be reported in kilojoules, which is 1,000 joules, or kilocalories, which are 1,000 calories. This kilocalorie is the same as a capital C-A-L-O-R-E, calorie. Alright, and that's the one we're used to when we're talking about food and things like that. So there's 1,000 joules in 1 kilojoule, 1,000 calories in 1 kilocalorie, and in 1 kilocalorie there's 4.184 kilojoules, just like in 1 calorie there's 4.184 joules. So when we put molecules together and they react, basically what we're doing is we're breaking bonds in the reactants, and then we're forming new bonds in the products. And so when we break bonds, typically we have to put energy into this system. Breaking that bond, for example, in chlorine, it takes 58 kilocalories per mole in order to break the bond between the two chlorine molecules. Forming the bond, so if we're going to add these two things together, is going to release 58 kilocalories per mole. So to break the bond, I've got to add energy. To form the bond, I'm going to release energy. So delta H, okay, is the heat of reaction, or the change in enthalpy. Okay, enthalpy is synonymous with heat. And a delta H, the delta means change in this case. So delta H is how much energy is going to be given off or absorbed in a reaction. If I absorb the energy, it's said to be an endothermic reaction because I put energy into the reaction. So that's endothermic. When I do that, the delta H is positive because I added energy to the system. When I release energy, it's said to be exothermic because energy is exiting the system. The change in energy, or delta H, is negative because I removed energy from the system. So when I'm making the bond, or when I'm cleaving the bond in the first case, okay, I am having to put energy in, so that is an endothermic reaction. When I break that bond, I am going to release energy. When I make that bond, I'm going to release energy, and so that is exothermic. The bond dissociation energy is the change in enthalpy, the delta H, for breaking a covalent bond by equally dividing the electrons between the two atoms. Bond dissociations are positive. Okay, so a bond dissociation, that is a breaking of a bond, is an endothermic reaction. And so since it's positive, we write that as delta H is greater than 0, or it's a positive. So a hydrogen H2, and I break that bond, then I'm going to have to put some energy in there to tear those two things apart. So it takes 104 kilocalories per mole to break this bond and separate these two hydrogens. If I'm going to form a bond between the two hydrogens, then I'm going to be releasing energy because bond formation is exothermic, and so the change in energy is negative 104 kilocalories per mole. The stronger the bond, the higher the dissociation energy. That is, the more energy it takes to break the bond. So the stronger the bond, the more energy it takes to break the bond. When you compare bonds from elements in the same group, in the same column, bond dissociation energies generally decrease as you go down the column. So it gets easier to break bonds with that element as you go down. So in HF, for example, it has a high bond dissociation energy because it's got the strongest bond, as opposed to HI, and these are all in group 7A. It's got the lowest, so it has the weakest bonds. So it's the easier bond to break. The delta H also indicates to us the relative strength of the bonds broken and formed. If it's negative, more energy is released in forming bonds than it is to break the bonds. So the overall energy of the reaction tells us, was this something that produced energy, or was this something that it took energy in order to make the overall thing happen? The bonds formed in the products are stronger than the bonds broken in the reactants in the case of an exothermic reaction. So in the case of methane, methane is CH4. I'm going to burn that with some oxygen and form CO2 and water. The delta H is a negative 213 kilocalories per mole. So that means that this is an exothermic reaction, and I'm going to generate heat. Okay, this is methane gas, and like some things we burn is butane gas, and it basically does the same thing. And so when we add oxygen to it and give it a spark, it's going to give us energy back. When the delta H is positive, then there is energy that has to be put into to break the bonds, and so it's endothermic, and so that means that you have to absorb heat in the system. So just a summary of energy changes. In an endothermic reaction, so just kind of know the difference between these. In an endothermic reaction, you absorb heat. The delta H is positive because you're adding energy to the system. Bonds broken in the reactants are stronger than bonds formed in the products, and the products are higher in energy than the reactants. And if it was me, I would pick which one of these is easier for me to memorize, endo or exo. And just remember that the other one is the opposite. So what I mean is you can memorize half the information. Like if it's easier for you to remember the exothermic. Exo sounds like exit. So heat is released, given off. The delta H is negative because you removed heat from the system. The bonds that you form in the products are stronger than the bonds in the reactants that were broken, and products are lower in energy than reactants. Alright, so if you learn this about exothermic reactions, then if you have a question about an endothermic, then you just remember it's the opposite of what you learned from exothermic.